Okay, everyone. I am going to make a review video with the information that I posted in Discord, since there was no answer key provided, and I will probably post this to the Discord and hopefully to Canvas sometime around the beginning of next semester. But let's go ahead and get started here. These should be some basic differentiation rules. So for part one, A, we have y equals, and in parentheses, 2x minus 7 raised to the fourth power. This is just going to be a chain rule problem where y prime is going to be equal to 4 times 2x minus 7 to the third times the derivative of the inside is going to be 2. So y prime is going to be 4 times 2 is 8. 2x minus 7 raised to the third power. For B, we have y is equal to e to the, and I think that says pi over 4. I'm going to zoom in here just to be sure. No, that says x over 4. So let me fix this. That says x over 4. Wouldn't be very fun to do a derivative that didn't have an x in it. So my y prime is going to be e to the u times du dx. It's going to be 1/4 e to the x over 4, or if you prefer, you can write that as e to the x over 4 over 4. Either way is correct. For C, we have y equals 7x to the fourth minus 3 times the fifth root of x plus 2 over 5x squared. I'm going to take a step to rewrite these as one-fifth power there and negative second power there. So my y prime is going to be 4 times 7 is 28. Drop the exponent by 1. 1/5 times negative 3 is negative 3/5. Drop the exponent by 1. When I subtract 1 from 1/5, I get negative 4/5. Negative 2 times positive 2/5 is going to be a negative 4/5. It's going to be an x to the negative third. I'm going to try and rewrite it in the original form I was given, where this one was just the power. This one had a root, a fifth root, like that. And this one was like that. Okay. Moving on to D here. You can go back and view any of them and pause the video if you need to. Take some time to look at them. If you have any questions about anything that I'm doing, go ahead and schedule an appointment with me. This is all old Calc 1 stuff. So first thing I'm going to do is write this in the denominator, because this turns out to be u prime over u, where u is the thing inside the log. Then I'm going to take the derivative of this thing. Derivative of 2x is 2. Derivative of cosine x is negative sine x. That's my numerator. I'm not going to try and simplify that anymore. 2x e to the negative x. This is going to be a product rule. I'm going to have two pieces where my f of x is equal to 2x and my g of x is equal to e to the negative x. So my f prime of x is equal to 2 and my g prime of x is equal to negative e to the negative x. And my product rule, if this is y, is equal to f of x times g of x. Remember, your product rule was that the derivative is leave the first alone and differentiate the second, plus the second times the derivative of the first. So we're going to leave the first alone and differentiate the second, plus, and then we're going to leave the second alone and we're going to differentiate the first. We use parentheses again just to be consistent. And like you get with exponential functions, sometimes there's going to be that exponential piece in both of them. So I can factor a, and this is the positive piece, this is the negative piece. I can do that, or I could have factored out a negative if I wanted to and made this that. Pick your poison, it's the same thing. But remember that if you're going for where are the zeros of the derivative, you're probably going to want one of these two forms right here. You're not going to get any zeros from e to the negative x, because remember that it looks like this, and it approaches 0, but it never gets there, right? So you're not going to have any zeros from this piece. Your only 0 would come there. So there would be a critical number at x equals 1 here. This is just all reminders of stuff that we've talked about. They're not being asked, you're not asking to do that in this problem, but just why would we want a factor? We'd want a factor so we could answer those questions that we talked about in applications of derivatives in chapter 3 of your calculus textbook. That was E. Let's look at F. And this is kind of interesting. Tangent of 3x. The denominator is root 4 minus x. So this is going to be a quotient rule where we have f of x over g of x. So our f of x is equal to tan of 3x. Our f prime of x, derivative of tangent, is secant squared. Then I have to multiply by the derivative of the inside, so that's going to be 3 secant squared of 3x. G of x is equal to, and I'm going to call this 4 minus x to the 1/2. So my g prime of x is going to be, there's going to be 2 of these down here. The derivative of the inside is -1. I'm going to fix this because I used a rule that I told you guys about in the tutorial videos that we did that I told you. I'm just going to write it down here with a star next to it, that the derivative with respect to x of the square root of u is going to be u prime over 2 times the square root of u. So we talked about that this is just one that comes up so much that you might as well just learn it as like a special rule. So again, we're going back to the quotient rule now. The derivative of y, here we're going to have to use the quotient rule. We're going to have to differentiate the top, leaving the bottom alone, minus derivative of the bottom, leaving the top alone. all over the bottom squared. So I know myself, and I know that I need to write that bottom squared part first, or I'm going to make a mistake. So bottom squared, that's that. Now I have to do the part where I leave the bottom alone. Minus, I need to leave the top alone. Okay, so the derivative of the top was 3 secant squared 3x, and the derivative of the bottom was a -1 over 2 root 4 minus x. That is really ugly. We don't like that at all right now. So we're going to multiply top and bottom by a root 4 minus x right now to get rid of this root 4 minus x. And while we're at it, let's just get rid of that entire denominator. Let's multiply top and bottom by 2 root 4 minus x. Let's get rid of this complex fraction here. 3 times 2 is 6. Root 4 minus x times root 4 minus x is 4 minus x. Minus minus is plus. Denominators cancel there. Two, and then 1.5 is 3/2. Okay, let's see if we can simplify the top at all. I don't know if we can. I think it might be worth it here to try and change these into 1 plus tangent squareds and then distribute and see if we get a quadratic that we can simplify a little bit. Because again, we might want to get it in fully factored form to answer some questions later. So this is going to be 24 minus 6x over here. This is going to be 1 plus tangent squared of 3x here. And, oh, yeah, I'm in good shape. Let's just keep going here till I get to a point where I'm either completely stuck or it's fully factored. So 1 times 24 is 24. 1 times -6x is -6x. 24 times tangent squared is 24 tan squared. -6x times tangent squared is -6x tan squared. Not sure this is getting me anywhere useful. Over 2. Yeah, this is not looking helpful. I was thinking that this piece and this piece and maybe this piece were all gonna do something fun and interesting, but it doesn't look like they're going to. So given that the problem here just asks for the derivative, undo that. I think we're good to probably leave the answer right to not worry about this stuff here. And I think we can leave it like that right there. Okay. Let's move on to G. Remember, not everything in calculus is going to come out to be a pretty answer. So my y prime, the derivative of cosecant is negative cosecant cotangent times the derivative of the inside that's going to be 4e to the 4x negative cosecant e to the 4x cotangent e to the 4x. That one seemed easier than the last one. All right. H. Y equals ln 4x cubed minus 2x to the third. And this is just a booger of a problem. And it would be a lot nicer if this thing on the inside were cubed, but it's the ln that's cubed. So this is a big chain rule problem. So y equals outer function 3. And then we've got ln 4x cubed minus 2x. And that's all going to be squared times the derivative of this inner function. So that's going to be 1 over u times the derivative of the inside here is going to be 12x squared minus 2. There's going to be some simplification that can be done there. And anything more? I think that's it. So we're going to simplify here and say that this is 3 times 6x squared minus 1 over 2x to the third minus x times ln of 4x to the third minus 2x squared. So that is you can factor some more if you want to. I just really don't think that there's no way that 6x squared minus 1 has any factors in common with 2x cubed minus x. Even if I pulled the x out here, that's going to be 2x squared minus 1. Both of those are giving me roots that are not alike in any way, so I'm not worried about common factors there. Like that. Okay. J. No, I. I need to do I before I do J. I just am zoomed out a little bit, or zoomed in a little too far. Let's see, e to the 4 root x. So my derivative here is going to be e to the u du dx Let's just write it off to the side since this is a little more complicated than what we deal with normally. So we're going to write this down because it doesn't change, times this derivative here. And I'm just going to go ahead and write that as that 2 has a positive exponent. There's a square root of x here. We might want to rationalize the denominator for some reason. If we do that, we're going to get that. You could see either this answer or this answer. We understand that you know to rationalize denominators if you need to. There is no need to rationalize the denominator there, but we rationalize denominators so that we don't miss any common factors that cancel out. Is the main reason we do it. J, y equals 4e to the x sine of x. So we've got a product rule in the numerator. So let's just go ahead and write it out as we're going to have y prime equals 4 is constant, the e to the power stays, and we're going to have the derivative of the exponent. That's going to be a product rule. So we're going to leave the first alone, take the derivative of the second, plus leave the second alone, take the derivative of the first. When I have sines and cosines together like this in a sum, I usually pull out the cosine. And then I leave this as something like this. And these are just getting more complicated, but these are all things that we did in Calc 1. There's not a single thing that we've done here that you shouldn't be able to take the derivative of. So this is y equals. I'm just going to go ahead and rewrite. Like that. That is not prime yet. That is my fault. Okay. So now I'm going to take the derivative. It's going to be 24x to the third. Negative 4 times the negative 1/8 is going to be a positive 1/2. X to the negative fifth. Negative 1/3 times a positive 2 is a negative 2/3. 2x minus 1, negative 4/3. And then I need times the derivative of the inside is 2. This is y prime is 24x to the third. It's 1/2 x to the negative fifth minus 4/3. 2x minus 1 to the negative 4/3. I think that's good enough. You can try and write this back this way if you want to take that down. That's a 3. That's a 5. This is where it gets tricky. if you try and rewrite this, do you make this a 1 on the outside? And you can do that. You can make this 2x minus 1 and then another cube root of 2x minus 1. You can do that, or you can put 4 of them on the inside. It doesn't matter. It's the same thing. It's safer to put them all on the inside since you don't know really well right now when you need absolute value bars for even roots. We didn't talk about that a whole lot. And let's look at L. This is your last one in this derivative section. L is going to be y equals 2 over 3x squared minus 1 squared. It's 2, 3x squared minus 1 to the negative second. So y prime is going to be negative 4, 3x squared minus 1 to the negative third times 6x from the derivative of the inside there. So y prime is a negative 4 times a positive 6x is a negative 24x. This is all in the denominator. 3x squared minus 1 to the third, like that. So that's it for the derivative piece. I'm not quite a half hour in. I'm going to clear all this that I just did, and I'm going to start talking about some of the integration things. So zoom back out. Now, as I said when I posted this, some of these things you're going to be able to integrate. Some of them you're not going to be able to integrate. So A, you're going to be able to integrate using your basic power rule. Integral of 3x to the fourth minus the cube root of x squared plus 2 over the 7th root of x, all of that dx. We're going to rewrite all those with powers, like this. And then you should be able to split it up piece by piece, like this. And use your simple power rule on each piece. Raise the exponent by 1, divide by the new exponent. Raise the exponent by 1, divide by the new exponent. We'll talk about what to do with that fraction in the denominator in just a second. Raise the exponent by 1, divide by the new exponent. Where you're dividing by a fraction, multiply by the reciprocal. That 2 and that 6 are going to reduce to make a 3. Something like that. Okay. B is a really good example of something that you can't do with your basic rules. Okay. In fact, that exact problem is going to come up later on the paper. No can do. Not a basic form. And U substitution won't work here. Why won't it work? Because I have U as x squared. Du is going to be 2x dx. I can't do anything right now in Calc 1 where I can add x's into the problem and make it work. So B is one of those no can do problems. C, though, I think we should be able to do this one. Let's see, 4 sine of 2x dx. Well, got two ways that I can do this. Let's go ahead and think about the derivative of 2x is going to be 2 dx. I'm going to save one of the 2's from the 4 and make this where this is u and this is du here. So this is going to be 2. The integral of sine is going to be negative cosine. We're going to evaluate that from x equals 0 to x equals pi over 6. That's going to be negative 2 times the cosine of pi over 3. Cosine of pi over 3 is 1/2 minus the cosine of 0 is 1. So that's negative 2 times a negative 1/2 is a positive 1. There's another way that we could have done this, or we could have broken this up into a 2 sine x cosine of x. 2 times 4 would have been 8 that we would have pulled out, and we would have let u be sine, and cosine x dx would have been, and we would have made this sine squared over 2, and we would have had to deal with sine squared, and it would have been equivalent but a little different. So I was able to just deal with it the way that it was written. But that's one of the fun things about trig integrals, is that you can deal with them multiple ways. Sometimes your answers will look different. E to the negative x over 3 dx here. So I need a negative 1/3 to deal with the du here. So that means I need a negative 3 to balance that out. That's a negative 3 e to the u du is going to be a negative 3 e to the u plus c. Negative 3 e to the negative x over 3 plus c. Ooh. E is a fun one, but not one we can do yet. So not a basic form that we can do yet. We'll learn how to do that one in particular really pretty early on in Calc 2 with f. 4x to the third is 3x over 2x squared. This is a problem for us because the degree of the top is greater than or equal to the degree of the bottom. But lucky us, we have a monomial. We're going to be able to split it up like this. We don't have to do long division here. Yay. This is a 3. We're going to get a problem, I think, in a little bit, though, where we are going to have to use long division. So this is going to be a 4 divided by 2 is 2. X cubed divided by x squared is x. We're going to have a negative 3/2 there with an x in the bottom. I'm going to split up each piece individually here now. And we're going to call this 2 integral of x dx minus 3/2 integral of 1 over x dx. This is going to be 2x squared over 2 minus 3/2. This is going to be ln of the absolute value of x. And we have x squared minus 3/2 ln of x plus c. That was f. Let's do g if we can. G is secant 4x tangent 4x plus 3 secant squared x over 5 dx. So I'm going to look piece by piece here. Secant 4x tangent 4x, that's almost the exact derivative of something. That's almost the exact derivative of something as well. Let's change colors here for a second so you can see what I'm doing. So the problem here is that I've got 4x and I never took the derivative of the part with the 4. It needs to be a 4 dx on the inside there with a 1/4 on the outside to match it. So that's going to be a secant u, tangent u, du here. And that's going to become it's going to become that. And then similarly here, this is going to be derivative of tangent as secant squared, but I'm going to have the derivative of the inside as well. So got to balance that out. Okay. And now h is interesting because we're not going to deal with it in its original form. We are going to bust it apart here. Like this. And then we're going to split each of those up. Like that. It's going to be x squared over 2 from 1 to 4. X to the 3/2 times 2/3. 1 to 4 plus x from 1 to 4. So this is going to be 16 minus 1 is 15 over 2. This is negative 4/3 times 8 minus 1 is 7. And 4 minus 1 is 3. So let's make these all over 6. That is going to be 45. 28 times 2 is 56. Plus 18 is going to give me 63 minus 56 over 6, and that is 7 over 6. So 7 over 6. All right. That was H. We're on I. Square root of e to the 3x. This one looks more complicated than it is. Remember that this is this, and when I raise a power to a power, I multiply the exponents. So I just need to have 3 halves here and 2/3 out there. 2/3 e to the 3 halves x from 0 to 1. 2/3 of e to the 3 halves minus e to the 0, which is 1. And that's sufficient to just leave it like that. Moving on to J. J, we've talked about something like this already a little bit. So the derivative of tangent squared is secant squared. So let's write this as tangent squared. You wouldn't normally think about this as being an ln thing, but no, let's not do that. That's not going to be it, because that's not a tangent to the first. Yeah, that'll work. Okay. I need a 3 and a 1/3. Okay, so what I have here is my u is tangent of 3x. My du is going to be 3 secant squared of 3x. And my n in this case is going to be a -2, because it's the denominator down here. So that's going to be a u to the n du situation. I've just got the 1/3 out front. So that's going to be 1/3 u to the n plus 1 over n plus 1 plus c. So 1/3 u to the negative first, well, that's just going to be a cotangent over -1. So that's going to change the sign here. So that one was harder. You might think about more problems like that in Calc 2, but there was nothing really keeping you from doing that problem with what you knew in Calc 1. It's just a little mental exercise. Well, let's look at K here. Cosine of the square root of x dx. You can do it, but you're not going to like it. I'm going to go ahead and do it for you, but you're not going to like what the answer to this problem is. So this is, let's see. Can I? Let's try it. So let's try a couple things and see if we can do anything. So this is cosine of the square root of x. So u is going to be square root of x. Du is going to be 1/2 square root of x dx. Nope, that's not going to work. What if I took cosine of u squared? You don't know how to deal with that. You know how to do with cosine squared of u. So we're going to say, for right now, not a basic form. And we're going to say at this time that you don't know how to deal with K. All right? So that's the 1, 2. That's only the third one in this group that you didn't know how to deal with. Now let's look at L. L is two over 3 x to the second dx. I'm just going to go ahead and, while I'm at it, make this 9x squared dx and pull the 2/9 out. And I'm going to bring that x squared up like that. You know how to deal with this. This is going to be 2/9 x to the negative first over negative 1. So that's going to be negative 2/9 x to the negative first plus c, or negative 2 over 9x plus c. That was it for part 2. Let's keep going here. All right. We talked about this very function here. Consider e to the 2x. I think we talked about that one earlier, and we know that the derivative of it is this by the chain rule. So we could conclude that if we were going to take the integral of both sides and the constant was going to come across, that the integral of e to the 2x was going to be 1/2 of e to the 2x plus c. That could also be verified by u substitution, if you remember how to do that, but can also be understood by this, like we just said here. So that's a little review on some stuff you can do, but they're telling you that you can only use that technique that they're talking about there when the exponent is linear. And now we're going to get back to this. What's the derivative with respect to x of e to the x squared? That's going to be e to the u times du dx. That's going to be this thing. And we would be tempted to say, oh, well, I can just follow the pattern where I can divide by this part that I don't have right here that includes the x. Nope, I can't do that. If I try and say that this is equal to this, I've got a problem. And the way I know I've got a problem is I'm going to try and differentiate this side here and see if I get the piece that's over here. I won't, but I'm going to try it. This is a product rule. So I'm going to leave the first piece alone, and I'm going to differentiate the second. Plus, and I'm going to leave the second piece alone, and then I'm going to differentiate the first. Because I'm bringing that x up as an x to the negative first. So that's a negative 1, and then a power of negative 2, and I'm bringing it back down like that. So this and this will cancel. That there is not what I have on the left-hand side. So no, that is bad math to just try and make up a new rule where, oh, I just divide by the thing that I don't have there. Nope, it's a product. You can't do that. You're forgetting the product rule, right? Okay, so that is a mistake that some students make in Calc 1 and definitely in Calc 2. Let's talk about another common mistake here. I already told you how to deal with this one correctly earlier. When we talked about when the degree of the top is greater than or equal to the degree of the bottom, we split it up, or we use long division if we have to. And they're going to say, oh, well, there's bad math out there that we don't want you to do, where students try and just distribute the integral symbol over the top and over the bottom. Now we know that this should be, I'm going to do it right so you see the right math first. That is not what they got. Not at all, right? Bad math. You cannot distribute the integral symbol like that. Okay? Does not work. Still got about 10 minutes. I think I can finish up all of this here. So what was the original function that was inside of here? Find a function f of x such that that's true. Well, let's take the derivative of this to get back to f of x. So if I take the derivative of this, then I have two pieces that are a product, right? So I'm going to leave this piece alone. Then I'm going to differentiate this piece. And I'm going to add it to, I'm going to differentiate this piece and leave this piece alone. Like that. So this is going to be negative 3 times 3 is 9. X squared and x squared is x to the fourth. So, okay, you should be able to differentiate the right-hand side to get back to the left-hand side. Now, it's a little more challenging there. Let's see if we can figure out what this function is here. If we say that do we know how to do this? I don't think we know how to do this yet. We don't know how to deal with this extra x here. Okay, so we're going to learn that in Calc 2, but right now I don't think know how to deal with that. So you can't just say because this is multiplied x and this is multiplied x, you can divide them out. You can't do anything like that. We're going to have to do something called integration by parts here later. And yeah, I don't think we can do this one yet. Okay, so that's a Calc 2 problem. Whereas the first one was a very basic Calc 1 problem. Let's try the right-hand side though. Let's try it and see if we don't get something that's x times something. All right, let's try it. So this is going to be leave the first alone and differentiate the second, plus leave the second alone and differentiate the first. Derivative of the constant is 0. Like that. Let's pull the x out here. This is my problem. I guess I can do this. I take it back. Okay, so there's x on the outside. So this is going to have to be my f of x. If I just differentiate this and then set it equal to x f of x, and I divide the antiderivative by x, I should get f of x. That works out just fine. I'm sorry, confuse you. I was thinking too far ahead in Calc 2. All right, determine if the following are true or false. Got a few minutes left here. Consider this integral. Upon performing the substitution, the integral becomes sine u du. That's false because the du here is going to be 2x dx, not dx. So that's false. For the interval from negative pi over 2 to pi over 2, and they're including them, that 1 over secant, that would be cosine. No, not right at all. So this is going to be, we would rewrite 1 over secant as cosine, and the integral of cosine is sine, and it doesn't look anything like ln of secant. That's not right. So that one's also false. C is just you can't do that one. No, that's not right at all. So can't do that. You can't integrate each piece like that separately. That's not the rule. You're going to learn a rule called integration by parts. That doesn't work. We know it's not right because if we try and take the derivative of this thing, let's try and differentiate this. So we're going to leave this alone times that, and then we're going to differentiate this piece and leave that piece alone. That's going to be something that doesn't match what we had on the left-hand side. This is not true because the derivative of the top would be a negative 2x dx. So that's not right. It's not a du over u situation. We're going to have to use something called partial fraction decomposition there. And let's see what we can do here. Tell us to do I assume that this is 1/2 here, and that this is and they're telling us a formula that you don't know, but let's just call number 5 as we don't know how to do it. Okay, you should be able to do it with the formula that they give you, but let's just call it that right now you don't know what to do with that because you haven't studied the form of x e to the ax yet. We'll get to that. We'll get to how to integrate something like this in calculus too. Then the teacher gave a quiz here, and there was, again, that bad u substitution that we talked about earlier where they just divided by the thing they didn't have. This is an e to the x squared problem again, that they're not supposed to be able, here, you need to do it like this. So if it's 2x, I'll show you how to do it right, because I like to show you the right way to do things. So we're going to bring this up, and this is going to be a negative x squared. And then the derivative of this is going to be a negative 2x dx. So this is a negative e to the u du is a negative e to the u plus c is a negative e to the u is a negative x squared. So that's going to be a like that. Okay. Want us to find all positive differentiable functions that can be written as for that to be true, then the derivative of u of x is going to have to be 1. So they're going to have to be in the form of x plus a constant that I'm going to call not c, because c is already here. I'm going to call it a. Okay, so as long as the derivative of this is 1, we're in good shape. So it can't be any linear function because it specifically says that it's going to come out to have just this on the inside with no multiplier. And that's it for this review. I think we took just about an hour. It might have gone a couple minutes over, but that's really close to the time that I had for each study session. So, all right. We will come back probably and talk about number 5 down here at a later date. We can also come back and talk about some of these things up here that we couldn't do at a later date. I will post this video closer to the beginning of the semester to give you guys some time to work on these by yourself. You all have a good break. See you next semester. Bye.